Okay, so I'll just show you a short video which is going to make it more clear to you how exactly a corkscrew is rotated and how we determine the magnetic field because of it. Okay, so you'll see the corkscrew rotating and it will make more sense to you. Okay, so in this video, just think the direction in which the corkscrew is going, which is the downward direction, is the direction of current. Then the direction in which the corkscrew is being rotated is the direction of the magnetic field. Okay, so as I said, you are going to get the same answer from the right hand thumb rule. So I like it just to use one rule for each and every question. I don't like to learn 3 rules for 3 different questions. So I would suggest that just stick with right hand thumb rule. If you like the corkscrew rule, feel free to go with it. Okay, so I would say just use one rule so that you don't get confused finally when you have a couple of rules to work with. Okay, you're going to learn more rules in other chapters too, right? It's not going to be just right hand thumb rule. So keep that in mind. Okay, so this was the Maxwell's corkscrew rule. Okay, so now we're going to do magnetic field due to a current in a solenoid. So now what is a solenoid? How does the current flow through it? How does the magnetic field is? So I'll first tell you what is a solenoid. So the solenoid is basically when this one straight wire that we had, we turn it into a spring kind of a form. So like this. Okay. So kind of like a spiral. This is called a solenoid. Now this could be if the same wire has to be used and we want more number of turns, then what would happen here? I have 1, 2, 3, 4, 5, 6, 7 loops. Now if I want 10 loops with the same wire, so I would have to make the loops even closer. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Why do I have to make it closer? Because the length of the wire given to me is same. If I have to make it more turns, then I have to make the turns closer. Okay, great. Now let's read in your PPT. So it says a coil of many circular turns of insulated copper wire wrapped closely in the shape of a cylinder is called a solenoid. Why a cylinder? Look at this. This is a cylinder, right? And the solenoid is somewhat like this. This is what a solenoid is like. So it looks like it is fitted inside a cylinder. One end of the solenoid behaves as a magnetic north pole while the other end behaves as a south pole. So what does that mean? Does it mean that it kind of behaves like a bar magnet? Because think about it, we said that a bar magnet has a north pole and a south pole, and it's saying here that this solenoid, if this is my solenoid, this has also got a north pole and this has also got a south pole. So it kind of would act like a bar magnet. You would think about it, right? So let's see if it does or doesn't. So if I want to show you a solenoid connected in a circuit actually. So this is the solenoid. If I take this solenoid only, and obviously I have to connect both the ends. So to a battery. So here I have this battery, and like this it's going, right? So if I've connected this to the circuit like this, now I'm going to have to tell you to think about what I said about the right hand thumb rule. We had said that if we hold the wire so that our thumb points in the direction of the current, our fingers gives the direction of the magnetic field. Now, this rule, this is what is most important to understand how a solenoid works and what is the magnetic field around a solenoid. This right hand thumb rule can be used in the other way also. So if our thumb points in the direction of the magnetic field, then our fingers are actually curling around the current. Okay. So now I'm going to use this other variation of right hand thumb rule, which my thumb doesn't point in the current direction, but my magnetic field points in the current direction. Why is that? Because in a straight wire, the current goes in a straight line, right? In a straight current carrying wire, the current is going in one direction. Or if it's in a circular loop, we can still consider that one small point where it's same. But one small area in which the loop is like a straight wire. But look at the solenoid. It's so many. Now I have drawn a little less number of turns, but in real life, the solenoid is something like this. It's like continuous turns and very close together. So it's almost not possible to find that one region where it is completely straight. The wire is completely straight. So that is why because here we can't have a wire in which a current is, flowing straight in a straight direction. The current is flowing in a curved direction, so we use the curved part of our hands or the fingers to point in the direction of current, so our thumb gives the magnetic field. It's interchangeable. If the thumb is the current, fingers are the magnetic field. If the fingers are the current, the thumb is the magnetic field. Okay, so now look at this. You come back to the circuit that I have drawn. My current is flowing like this, right? The current is going like this. The current goes downwards like this. So what is the direction of my current? This direction of my current is like this. It is coming towards me. This loop, that first loop is like this, right? So if I move my fingers in the direction of the current like this, what would be the direction of magnetic field? Towards right? Right? Now, if I think, let me draw this again. This is coming out. So it is going like this. So like this. Okay. So this is the bulging out part. This part that I have just drawn, where I have drawn this arrow for the current, is the part which is coming towards me like this. And the other part, the second line that I have drawn, this one is what is going backward. So it's going like this. This is the loop. Towards me, away from me, towards me, away from me, towards me, away from me. So it goes like that. Okay. So now I'll complete the solenoid. Okay. Now think about it. First loop is coming towards me. So the current is like this in a curved direction. So where is the magnetic field? Right side. Okay. Now if we look at the second part of the same loop going away from me. So current is like this going away from me. So it is also towards the right hand side. Similarly, if we calculate the current, if we calculate the magnetic field using right hand thumb rule for each loop, we will see that the magnetic field is in this direction, right side, like this. So what can we do? We can actually show the magnetic field in one same direction for all loops. Why? Because we had said that because of 2-3 wires, if the magnetic field is in the same direction, it gets added up. So this is the direction of the magnetic field. Now, can you think about something like this that we've already seen? Like magnetic field is entering from one end, exiting from one end. The bar magnet, right? That is what I said in the beginning, that the solenoid might act like a bar magnet because it has one north and one south pole. This is how it acts like a bar magnet. So this would be the straight line that I had talked about, that is in the middle of the bar magnet, and the other field lines would be like this. Okay. Again, in this direction, exiting from one. So now tell me which pole would be which. Which pole is this part and which pole is this part? We had said that outside the magnet, the magnetic field lines go from north to south, right? That is, north is the exit and south is the entry. So look at this. Outside, where is it going from? Because it's going from here to here, we can say that it is curving like this and it is going into this pole. So obviously this is our south pole and this is our north pole. Okay, so now you know that a solenoid can actually act like a bar magnet, right? We didn't know it at the start. We drew the solenoid, we connected it to a circuit, we saw that the direction of current in each turn is like this and the magnetic field is pointing towards the right direction. Now if you change the polarity of the battery, what does that mean? If you place the battery, instead of positive negative like this, if you place it like this, negative positive, then you will see that the magnetic field is reversed. The magnetic field will be in the left direction. That is a homework for you that you can try for yourself. Okay. Now I have just shown you 2-3 magnetic field lines. You can show like you used to show for a bar magnet. Remember, in case of a bar magnet, from north to south, we used to, if I have to draw it like here are south, I'm comparing it to the solenoid, right? So you remember it used to be like at least 3-4 lines used to show, like 2 here, and then one straight line also. So you can show it like that in case of a solenoid also, because it is the same thing. Okay, great. So now I hope you know why I said that the solenoid also acts like a bar magnet. Now the solenoid is actually a very useful thing. What is it used for? We'll just see. Okay. So electromagnet. So let's read what your PPT says here. It says that a strong magnetic field produced inside a solenoid can be used to magnetize a piece of magnetic material. Now, if you remember, we had said that inside the bar magnet, you remember how the lines were. If we draw this as a bar magnet, inside it, the lines, magnetic field lines were very, very close to each other. So what does that mean? That inside the bar magnet, the magnetic field is very strong, right? But think about it. A bar magnet is a solid cuboid. It's like a solid piece of, say, cement, whatever it is. The magnet is solid. You can't put anything into the magnet. It is solid. It is filled. So we can't actually put anything inside in that region where the magnetic field is so strong. We can't reach it. We can only experience the magnetic field around the magnet. But in case of a solenoid, it is actually like this. It is like wound in the form of a cylinder. So it is hollow inside, right? So you can actually put something inside that magnet, and whatever the material that you put, it would be exposed to a very strong magnetic field. How? Look, this is our solenoid, right? I'm drawing it very big just so that I can show it to you. So if this was the current in it and I had shown it to you that this was the direction of magnetic field. So here the magnetic field lines are super, super, super close to each other. So they are very strong magnetic field. So very strong magnetic field is produced. So in this hollow region, if I put, say, a piece of iron, it can actually get magnetized. Now, what does magnetized mean? Magnetized means that magnetic properties are given to that piece of iron or whatever we put into it. So let's read in your PPT right now. It says that a strong magnetic field produced inside a solenoid can be used to magnetize a piece of magnetic material like soft iron. So this is an example that can be asked you, like give a material that can be used to magnetize, that can be magnetized inside the solenoid, that is soft iron. So what does this mean? Magnetize a piece of magnetic material. We know iron is magnetic. It gets attracted to a bar magnet or any other magnet. So it is magnetic in nature, right? So magnetize a piece of soft iron means that you give magnetic properties to iron, or you make the piece of soft iron into a magnet too. The piece of iron, it is attracted to a magnet, but it doesn't behave like a magnet, right? It doesn't have a north pole, south pole or a magnetic field. It just gets attracted to it. But if we put a soft iron piece inside the solenoid, it would also become a magnet. So that soft iron, so right, we write after magnetization. Magnetization is this process of putting that soft iron inside that solenoid so that it becomes exposed to that super, super strong magnetic field inside the solenoid, and it also starts behaving like a magnet. Okay, after magnetization, the soft iron starts behaving like a magnet. Now, because electricity was used to make this iron behave like a magnet, to make the soft iron behave like a magnet, and because it wasn't naturally a magnet, it wasn't originally in its original form a magnet, right? We made it into a magnet by exposing it to super strong magnetic field inside the solenoid. So because electricity was used to make the soft iron behave like a magnet, it is called an electromagnet. Okay, so this means that this also, again, we can write that the strong uniform magnetic field produced inside the solenoid turned the soft iron into a magnet too. That means the soft iron was not originally a magnet, right? When it was exposed to it. So because there is this space inside the solenoid, we can insert something inside. And now, why have I said uniform electric field? Because inside a bar magnet, if you come to this figure that I have made of a bar magnet, these field lines are actually parallel to each other, right? But if you go outside the bar magnet, these field lines keep getting more and more farther from each other, right? So that means outside the solenoid or outside the bar magnet, the magnetic field is not uniform. Uniform means that it is the same everywhere. So outside the bar magnet, is it the same everywhere? No. Be it a bar magnet, be it a solenoid, be it a straight current carrying wire, we have seen that with the increasing distance from that magnet or whatever is generating that magnetic field, the magnetic force or the influence of the field obviously decreases, right? If you keep a magnet here and you keep a magnetic material very far away from it, would it attract it? No, you have to actually bring it pretty close to attract it, right? So that is how, if I show you an example, here I have these earphones. Okay, so these earphones, these two earpieces actually have magnet holding them together. Look at this. When I bring them close, can you hear that sound? That is the sound of the magnets actually becoming joined. So if I keep them very far away, they won't attract each other because this magnetic field is around this only. This magnet's magnetic field is around this only. It is not very strong, very far away from it. So that is why only when I bring them close together, look, when I bring them close, they automatically get joined. Look at this. Here, there is no force that I can feel. They don't want to get joined because they are not near each other's strong magnetic field. But when I bring them close, they automatically get joined towards each other even if I don't put them together. So this is why we call the field inside a bar magnet or the field inside a solenoid constant and uniform, because there is no distance varying inside the bar magnet, right? Inside, all the fields are like this. All field lines are parallel to each other, and inside the field lines are very close to each other. So the magnetic field is the strongest. So if this is the solenoid, this is my solenoid, the magnetic field lines are like this here. Very, very close and parallel to each other. They are not increasing in distance like they are outside the solenoid. So we call it uniform. So this is how a soft iron piece can actually be converted. Something that is not even a magnet can be converted. But don't think anything can be converted into an electromagnet, right? You can't just put a piece of plastic inside and it will become a magnet. No, only magnetic materials. Like here it is written, right? A piece of magnetic material like soft iron is magnetized, not just anything. Okay, great. Let's move on. Now, the first question says that consider a circular loop of wire lying in the plane of the table. Okay. Let the current pass through the loop clockwise. Okay. Apply the right hand rule to find out the direction of the magnetic field inside and outside the loop. Okay, great. Okay, so we are going to break this down into small steps and we're going to see how the answer comes out. Okay, so the first thing that you have to keep in mind is that the loop is actually in the plane of the table. What does that mean? If this is our table, just think about any study table you have. The loop is actually on it, right? It is not standing, it is not vertical to it. Okay, so you have to keep that in mind. Great. So let's say that this is our table. Okay, this is our table. I've drawn a table only so that you can understand. And we have kept this circular loop like we had done in case of when we were finding the magnetic field due to it. We had done like this only. So this is our circular loop and it is connected to a current. So now it is saying that current is passing through the loop clockwise. What does clockwise mean? Clockwise means like this, right? In this direction. Clockwise is in this direction. This is clockwise direction. So it is passing through this. So if this is the direction of current, obviously our positive is here, positive of the battery. You may or may not show this because it does not tell you to show the complete circuit. So that is completely your choice. Okay. Now, it says apply the right hand rule to find out the direction of magnetic field inside and outside the loop. So I'm calling this region 1, which is the inside, and this whole region 2 is the outside. So we are going to break this down. First, we will just draw the magnetic field lines for point A. I'm just removing these and putting this here. Okay, so you just know the direction. This is point A and this is our point B. Okay, I'm calculating it at 2 points. So here at point A, now just think about this. If the loop is lying on the table, right? If the loop is lying on the table and our current is flowing like this, right? This is our table, this is our loop, and the current is like this. Then where is the magnetic field going to go? It is actually going to go outside the table and inside the table. We're not going to say clockwise, anti-clockwise, because here we have to tell the answer with respect to that plane of the table, right? We can't show the direction without telling that it's actually as if 3D, it's in 3 dimension, that it's coming out. Why? You won't be able to understand this till you just visualize it. Just think there is a loop lying on your table. You must be sitting on a table, on a bed, something, right? So just think if there is a loop on this table. So here I have my table. So I'm just thinking there is a loop on my table, right? There is a loop on my table. It has current in it, right? Now I am going to put my thumb in the direction of the current. Great. So which direction is my fingers going in? It is actually going like this. What does that mean? This is the table. My fingers are like it coming out of the table and then going into the table, right? So that is the logic that we're going to use here. So we say that applying the right hand thumb rule at point A, we can tell that because the direction of current is upwards, and this upward is not like this. Why? Because the loop is in the plane of the table and our table is like this. The table is flat, right? Take out your hands, do it with your hands only, then you will understand. Okay, so this is your thumb is in the direction of current because the loop is in the plane of the table. Okay, now think about this. This is my point A. Here my fingers are going like this. That means my fingers are almost going out of the table. That means at this point the loop magnetic field is actually coming out of the table, and then it goes a full circle. So if I draw the concentric circles that you have always drawn, I'll just draw 2, 3. Then you can say that in this direction it is somewhat coming upwards, right? So why I don't want you to draw it in a way like this, because it doesn't clearly show that the magnetic field lines are actually coming outside the table. So instead of drawing it like this, we will draw it like this. Okay, and here we can see towards the right side of point A, we can see if this is the current, the magnetic field comes out and it goes into the table towards the right side of the point A. So here we say downwards like this. Similarly, for point B, the current is in this direction, right? So what happens here? Again, you have to take out your hands, you have to point your thumb, and you have to see for yourself. Only then you will understand. Again, think, okay, this is my table. Here there is my loop. Current for point B is towards me, right? So I put my thumb towards me and then I see that my fingers are going like this. Very weird gymnastic I have to do, but this is how you will understand. You also have to bend your arm like this. Only then you will see how the magnetic field lines actually are. So think about this. My point B is here, and here my magnetic field lines are coming out of the table to the right of point B. So okay, I draw it. Okay, I draw it like this. And again towards the left of point B, how would it be? If my hand could completely take a 180, it would come back like this. It would go downwards. Look at this. My fingers would go all the way around and point downwards towards the right side of point B. So again, I point downwards here. Now, I mark these as region 1, 2, 3 and 4. So, I just write in my answer, I show this figure, okay? You have to show this figure, otherwise it would not be clear when someone is checking your answer, or even if you are explaining it to someone, why you have not drawn it in the normal way, why you have not drawn it in concentric circles. Because you draw it in concentric circles when it is in the plane of something. You remember when we drew the concentric circles in case of a straight wire, we had drawn it like this because the wire was perpendicular to that paper and the circles were actually on the paper. But right now, those concentric circles are not on the table. They are coming out of the table and they're going into the table. They're in the 3D plane, which you cannot show like that, which you cannot show in the form of these concentric circles. It would be wrong. Okay, so that's why you'll draw these lines, these arrows, and then you'll explain it in your answer. So I hope now it's clear to you why we have drawn these arrows. Now I'll tell you how we would explain our answer. So we would write that inside the loop first, right? It says inside and outside. So we say that region 2 and 3 are inside the loop, right? Look at this 2 and 3, they are inside the loop. Region 2 and 3 are inside the loop. So we say applying. Again, I write in short form, you write completely. You don't use short forms like this. I am writing using right hand thumb rule. Okay, I am writing RHTR. You write the whole thing, applying right hand thumb rule. We can see that in this region, inside the loop, the magnetic field lines or the magnetic field lines seem to be going into the table, right? Because it is not in the plane of the table. Again, think about it. If your loop is lying on the table, think about it. My table is here. I am looking at my loop. My loop has current like this. Obviously, in the plane of the loop, the current is there. And my right hand thumb rule says that if this is my current, this would be my magnetic field. So it would almost look like the field lines are coming out of the table and in the other side going into the table, right? I hope that is clear to you now. So the magnetic field lines seem to be going into the table. And outside, we know that region, which are the two regions which are outside? They are region 1 and 4. Okay, region 1 and 4 are outside the loop, right? Again, applying right hand thumb rule. Students will write it completely. We can see that the magnetic field lines are coming out of the plane of the table. Okay? So I hope this is clear to you. So you can say that the magnetic field inside the loop is going into the table, the plane of the table, and the magnetic field outside the loop is going out of the plane of the table. Okay? Let's move on now. So the next question says the magnetic field in a given region is uniform. Draw a diagram to represent it. Now, you just go back to what I had told you about uniform magnetic field, why we call the uniform magnetic field inside a solenoid and a bar magnet, and that is what we're going to use for this question. So, I'm just going to quickly draw a bar magnet. The question is not asking you to draw a bar magnet or a solenoid. You don't have to draw it, but I'm just drawing it to explain it to you right now, and then I'll tell you how you will draw it for the question given. Okay, so this is the bar magnet, this is the north and this is the south. I told you that inside the magnetic field lines are like this, right? We all know that because when we go outside, the magnetic field lines keep getting farther and farther. So obviously we know that outside the magnetic field is non-uniform. What does non-uniform mean? That it is not same at every single point. Obviously, magnetic field lines getting farther and farther, so strength of magnetic field decreasing. Very, very logical. Same in case of a solenoid. If this is our solenoid, it obviously behaves like a bar magnet we have seen. So the magnetic fields are actually like this. And we know in case of a bar magnet, outside the lines are from north to south and inside they are from south to north. Similarly, in the case of a solenoid, it can be in either direction. Say if this is south, then it is towards, it's from north to south, so this would be a north, this would be a south. So, what can you see is the common thing in case of uniform magnetic fields? We can see that the field lines are in the same direction, right? And we can see that the field lines are parallel and close to each other, right? So even if they aren't close to each other, even if the field lines are a little far from each other, uniformity means that they're in the same direction and they're parallel to each other, right? So that is how we're going to start our question. We are going to first tell them that we know what uniform field lines means. Okay, so we say that uniform magnetic field is present in a region when field lines are, this is the symbol for parallel, you write the word parallel, and in the same direction, right? So these are the two important things. They have to be parallel and they have to be in the same direction. That is when the magnetic field is called uniform. So how do we represent it? You write therefore, we represent it as this. Okay, so look, this is the direction. They all have to be in the same direction. They all are parallel. So we say that this is a representation of a uniform magnetic field. Okay. Okay, let's see the next question. So it asks, choose the correct option. Okay, will do. The magnetic field inside a long straight solenoid carrying current is A, 0. B, decreases as we move towards its end. C, increases as we move towards its end. And D is same at all points. Okay, let me draw solenoid. So by this time you should know the answer, but I'm just drawing it again. So we know that inside the solenoid, the lines look something like this. So what does this say? We just did it in the last question. We said that when the lines are parallel like this and in the same direction, solenoid is like a bar magnet only. So inside a bar magnet, is the magnetic field uniform? Yes, because it's in the same direction and because it is parallel. So inside a solenoid, is the magnetic field 0, decreases, increases are the same? The correct option is same at all points. And if you want to give an explanation to it, you give the same explanation as the last question, that because the field lines are parallel and because they are in the same direction, the magnetic field lines are in the same direction, the magnetic field inside a solenoid is uniform. Okay. So this was all about, we learned about the current carrying loop, how we calculate the current because of it. Then we learned about a solenoid and how the current is through a solenoid. We learned about an electromagnet also. Okay, so make sure all of these concepts, applying the right hand thumb rule, using it in different situations like a solenoid, like a straight wire, like a circular loop, that question where the magnetic field lines were coming out of the table, all that are very, very good applications of the right hand thumb rule. What is a uniform magnetic field? That also. So make sure all of these concepts are thorough to you, because as we go forward in this chapter, all of these small concepts are going to use at the end also. So don't think that once you're done with the right hand thumb rule, it's not going to be used. It is going to be used till the very end of the chapter. Okay, so make sure that all of your concepts are thorough at every single point, so that it's not a very huge burden for you to do all of it at once at the end of the chapter. So in the next class, we're going to do force due to the magnetic field. Okay, so make sure you come revise with all of your chapters and all of your topics. So I hope you enjoyed this, students. Thank you and take care.